Welcome to the fifth lecture of this course, Transportation Network Analysis. So, in the last class we had started to discuss about complete matching problem. So, let us now see how to formulate it as an optimization problem. So, in the similar way as we have seen for the other optimization problems before this optimization problem can also be formulated as an integer linear program. So, let us define the decision variable that we will be using in this optimization formulation. For every edge ij that belongs to this set capital E, let xij be equal to 1 if ij is in the matching and 0 otherwise. So, then we can present the integer program as follows. So, you can see that these decision variables xij are kind of in the similar manner as we have been seeing some other optimization problems. For example, in the travelling salesman problem also we had these decision variables xij which were equal to 1 if edge ij was selected in the solution and 0 otherwise. So, this is in the same way as we have seen before. So, the objective function of this complete matching problem is to minimize this summation Cij Xij, where again the summation is going through the set of all the edges capital E. And then we have this first set of constraints which is saying that for every node I that is present in this set capital A, summation Xij is equal to 1, but here we need to pay close attention to how the summation is going. So, the summation is only over through those set of nodes j that belong to the set B for which there is an edge that goes from node I to node j. Okay. Similarly, we have this set of constraint here which is saying that for every node j that belongs to the set B here, summation xij is less than or equal to 1, and here the summation is going through all the nodes I in set A for which there is an edge that starts from node I and ends in node j. Okay. And then we have these constraints that xij are binary. So, let us understand these first two constraints through an example here. So, we have 5 nodes here. Nodes 1 and 2 are the part of this set capital A, and nodes 3, 4 and 5 are the part of this set capital B here. And suppose we have selected this edge which is going from 1 to 3 in the matching, and suppose we have selected this edge. Okay. So, you can see that for node 1 there is exactly one edge that is incident on it and that is selected as a part of this matching, and for node 2 also there is exactly one edge going from 2 to 5 which is incident on node 2 and that is selected as part of this matching. And for the nodes that are belonging to the set B here, that is nodes 3, 4 and 5, there are at most one edge that is incident on each node and that is selected here. For example, for nodes 3 and 5, each one of them has exactly one edge that is incident to it and that is selected in the solution, and for node 4 there is no such edge that is incident on it and is selected in the solution here. So, let us take a look at this set of constraint here. So, what it is saying, for every node I in A. So, if you look at this node 1 here, so it is saying that you have to do summation xij equal to 1, okay, but we do not have to do this summation j over all the nodes in set B. We have to only do the summation over those set of nodes in this set B here for which there is an edge starting from node 1 and ending in the set in the node belonging to the set capital B here. So, for example, we have an edge starting from node 1 and ending in node 3 here. Similarly, we have an edge starting from node 1 and ending in node 4 here. Okay. So, we will be only doing the summation for nodes 3 and 4 here, okay, because since there is no edge that is starting from node 1 and going to node 5 here. So, in this summation when I is equal to 1 here, so then we do not need to sum this j for node 5 here, I mean. So, the j will only take values for node 3 and 4, okay. Similarly, if we look at this set of constraints, so when we are doing this summation here in this constraint here, and this node j is the node 5, so then we will be only considering I to take the value 2 here and not 1. Okay. So what it means is that x 2 5 is less than or equal to 1, okay, when we have node j as 5. Okay. Similarly, if we were looking at this set of constraint and this node I was node 1, so as I had explained, this constraint means that x 13 plus x 14 is equal to 1. Okay. So either you select this edge 13 or you select edge 14. You cannot select both of them in this final selection here. That is what it means. Okay. Okay. So this was the optimization formulation for the complete matching problem. So now we will be taking a look at another very important class of problems called scheduling problems. So these problems are also type of combinatorial optimization problems because the total number of solutions that are possible are finite, and these kind of scheduling problems arise wherever we have to execute a set of tasks, or sometimes they are also called jobs, and they have to be executed on several processors or machines subject to constraints such as priority constraints of a task over another, deadline constraints, and so on. Okay. So for example, to give you very easy case, suppose you have 3 tasks that need to be done and there is a single machine, okay, and you can only process a task, you can only process one task at a time on that given machine or processor. So in which sequence should you say process them so that some objective is reached? Now it can happen maybe that the order in which a particular task is executed might also determine how much time it takes to execute that. So if that happens, then the sequence in which you execute these tasks will determine how much time it will take in the end to execute all of these tasks. Okay. So if the objective is to suppose minimize the total time it takes to minimize all of these tasks, then determining which sequence in which you should execute this task is important. And there can be several constraints here. For example, some of the tasks can have particular priority over another task, so they might need to be completed before other tasks can be done. Similarly, there can be some deadlines. For example, a particular set of tasks need to be completed maybe by a particular set of deadline here. Okay, so as with any other optimization problem, this scheduling problem has the goal of minimizing some objective function. For example, it can be the total processing time, that is the time between the beginning of the execution of the first task and the end of the execution of the last task. And the applications of scheduling problems are wide ranging. For example, it might be the scheduling of tasks on different machines in industries. It could be scheduling of damaged roads after disaster by repair agencies. Okay, so for example, after a disaster, suppose there are multiple roads that are damaged or they are blocked. So if you only have a particular repair agency and it can only repair one road at a time, so in which sequence should it go so that it attains some objective? For example, the objective could be to minimize the total system travel time during that repair duration. So since the blocking of every road creates some congestion on the network, so the sequence in which maybe you unblock these roads might have an effect on how much final travel time that might be experienced by the network. So in that kind of problems, determining the sequence is important. Okay, so in this course we will be considering a typical scheduling problem. So we are given a task set system here, which is denoted by this set V here, and there are n tasks here. For each task ji, we have an integer processing time tau I given to us. Okay, and these tasks are to be executed on m processors. So for all pair I and j, we have the set of parameters aij that are given. So these parameters aij are binary. So they determine whether or not a task ji can be executed on the jth processor or not. Okay. So it can be the case that some of the tasks may not be possible to be executed on a particular set of processors. So those kind of constraints might also be present in the optimization problem. So those kind of restrictions will be provided into the problem. So if aij is equal to 1, then task ji can be executed on the jth processor, otherwise not. Okay. There is also a deadline di associated with the task ji. Okay, so it might be the case that ji needs to be completed at most by di time units after the beginning of the first task. Okay. Finally, we can have the set of precedence constraints here, which are represented by this directed acyclic graph. So you see that there is a digraph written here. A digraph with no cycles is called a directed acyclic graph here. Digraph is the short form for directed graphs. So to give you an example, for example, if there is a disaster, then suppose there are some infrastructure components that are damaged. Now for particular kind of infrastructure components like hydraulic power plants and so on, before repairing them, it might be important to first repair the power infrastructure in that area. Okay. So these kind of restrictions are represented by these precedence relations, that before executing some task, it might be required to execute some other tasks. Okay. And again, it needs to be understood that why we should not have any cycles in this directed graph that is there. Let us consider a case where you have cycles. For example, there is an edge that starts from task 1 and goes to task 2. Similarly, there is another edge that starts from task 2, goes to task 3, and then there is another edge that goes from task 3 and ends in task 1. Okay. So what do these edges mean? It means that task 1 should be completed before you can start task 2. The other edge says that the task 2 should be completed before you start task 3, and the last edge says that the task 3 should be completed before you start task 1 here. So you can see that there is kind of a cycle here. So it is not possible to start any task because something else or some other task needs to be completed before that, and therefore in that situation it is not possible to execute any task, and therefore we will be assuming that the directed graph that is present to represent these precedence relations between these different tasks here is acyclic. So there are no cycles that are present. So let us now define the decision variables here. So let Si be the starting time of job or the task Gi here. Okay. And without loss of generality, we can assume that SIs are integers and the minimum value of Si is 0. What minimum value of Si equal to 0 means? That we will be starting our clock to, and we will be setting t equal to 0 at that time at which we start to execute one of the, for the first task that we execute. Okay. Okay. And another decision variable that we will be defining and very important is Pij. So this is a binary decision variable. This is equal to 1 if task Ji is executed on processor J and 0 otherwise. Okay. And let this small f be the finishing time of the schedule. What does the finishing time of the schedule means? That it is the last time at which a task gets completed. Okay. Let us maybe take an example to understand this. Suppose there are two processors and we have some tasks here. So we have these tasks A, B and C, maybe they take the time 1, 4, 7 respectively. Similarly, we have another set of tasks D and E. They are executed on another processor, maybe this one takes time 8 and this one takes the time 1 unit. Okay. So this set of tasks is being maybe run on the first processor and this set of tasks will be executed on the second processor. Okay. So for the first processor, these tasks will complete after the end of 1 plus 4 plus 7, this is equal to 12 units. Okay. And the second set of tasks here, which is executed on the second processor, will take 8 plus 1 equal to 9 units. So the last time at which any task ends will be at the 12th time unit. Okay. So, by that time the second processor would have executed everything, but this first processor would have just ended executing its last task. So, f will be equal to 12 in this case. Okay. So, that is the finishing time. So, we want to minimize that finishing time. Okay. So, the last time at which any task gets executed on any processor here. So, the objective is, as I mentioned, to minimize this finishing time of the schedule subject to the constraints that will be described next. The first constraint is that summation Pij is equal to 1 for all I in 1 to n. Okay. So, what this constraint is saying that every task Ji should be processed on exactly one processor. Okay. That is why there is a sum which goes from j equal to 1 to m. Okay. And if you recall, we also have these parameters given to us represented by Aij, and they provide some restrictions on what tasks can be implemented on what processor. So, if it is given that Aij is equal to 0 for a pair of tasks Ji and a processor J, so then you cannot execute the task on that processor. Okay. And only if Aij is equal to 1, then you can process task Ji on the processor J. Okay. So, when we are solving this optimization problem, so Pij should then only be 1 in those cases where where Aij is equal to 1. Okay. So, it can happen that maybe Aij is equal to 1 for a pair Ij, but then Pij can be equal to 0, that is okay. So, we may not execute a particular task Ji on a processor J even if Aij is equal to 1, that is, it is possible to execute that task on that processor. However, if it is already given that it is not possible to execute the task on that processor, then Pij cannot be equal to 1. That is what we would need to ensure here. Okay. And in order to ensure that, we have this constraint now. So, this is saying that Pij is less than or equal to Aij for all Ij here. So, if Aij is equal to 0, that is, it is already given that you cannot process that task Ji on processor J. So, then Pij cannot be equal to 1, it has to be equal to 0. Okay. But if Aij is equal to 1, then Pij can be both 0 or 1. Okay. Okay. Another constraint that is there is that no task can be executed simultaneously on the same processor. That is important. So, we want to express the fact that whenever Pij and Pkj are both equal to 1, that is, we are executing tasks J and Jk on this processor J, and it is given that task Ji executes before Jk, then Si plus tau I should be less than or equal to Sk. Okay. So, that means that the starting time of task Ji plus the processing time of task Ji should be less than or equal to the starting time of job Jk. Okay. So, you should have completed this task Ji, and only then you can start the other task Jk here. Okay. If it is given that both of these two tasks are executed on the same processor and task Ji executes before Jk. Okay. So, in order to represent this constraint, we will be using a constant m here, which is taking value in this open interval 0 to 1. We also have this value capital T given to us, okay, which is the sum of the processing times of all of the jobs that are present. There are n jobs here. Okay. So, what does this mean here? So, this is the capital T is that amount of time it will take to process all the jobs if you just had a single processor. Okay. So, if you execute all the jobs just one after the other on a single processor, capital T is that time. Okay. So, for example, let us just see an example here. So, suppose you have these 3 tasks. The first task takes maybe 2 time units to process, the second one takes maybe 3, and the third one takes maybe 1 time unit. Okay. So, if you process all of these 3 tasks just one after the other on a single processor. So, it will take 2 plus 3 plus 1 equal to 6 time units here. Okay. So, capital T is equal to 6, and let us define another useful variable delta Ik, which is a non-negative integer variable which is equal to 1 if Si is less than Sk and 0 otherwise. Okay. So, we will be using this variable delta Ik in order to define this constraint that I had shown in the last slide, that if two tasks are being processed on the same processor and the starting time of one of the tasks is lesser than the starting time of the other task, then the first task should complete before you can start the other task. So, before coming to that constraint, let us define this delta Ik. Okay. So, we will be defining it in this way, that so the definition delta Ik is that it is a non-negative integer value if Si is less than Sk and 0 otherwise. So, this is the set of constraint, that is Sk minus Si is less than or equal to delta Ik times capital T for every pair Ik here where I is not equal to k, and Si minus Sk plus small m is less than or equal to 1 minus delta Ik times capital T. Okay. So, let us understand how do these constraints define this variable delta Ik. Just remember what do we want from delta Ik. It is a non-negative integer variable which is 1 if Si is less than Sk and 0 otherwise. Okay. So, here if you look at the top inequality here, if Sk is greater than Si, then the top inequality ensures that delta Ik is equal to 1. Why is that? Because when Sk is greater than Si here, then this LHS of the top inequality is positive. So, then delta Ik cannot be 0, it has to be equal to 1. Okay. And why we have multiplied capital T here? Because Sk minus Si, the starting time of job k minus the starting time of job I, can never exceed capital T. Okay. Why is that? Because capital T is the total time it will take to process all of the tasks if you process on a single processor. Now, here you can have more than one processor. So, you can never have the starting time of one of the tasks minus the difference of the starting time of another task to be greater than capital T. And that is why we have introduced capital T here, because Sk minus Si can be something greater than 1, but delta Ik can only take 1 as the positive value. So, that is why we multiplied capital T so that this constraint is satisfied. Okay. And note that this constraint does not put any restriction on delta Ik if Sk is less than or equal to Si. So, if Sk is less than or equal to Si, this top constraint will be less than or equal to 0. So, in that case delta Ik can either be 0 or 1, and that is why we need the second constraint to ensure that delta Ik is equal to 0 when Sk is less than or equal to Si. So, the second constraint will ensure this. So, let us look at the second constraint. So, if Sk is less than or equal to Si here, then here the LHS of the bottom constraint is a positive quantity, because we have defined small m to be a constant which lies in the interval 0 to 1. Okay. So, then delta Ik cannot be 1, otherwise this RHS of the bottom quantity, bottom inequality will be 0. So, delta Ik is forced to be 0 in that case, and this constraint, this bottom inequality does not put any restriction if Sk is greater than Si. Okay. Why is that? Because we have assumed that the starting times here are integers. Okay. So, if Sk is greater than Si, Si minus Sk has to be less than or equal to minus 1. Okay. And since m is lying in this open interval 0 to 1, so therefore, this quantity Si minus Sk plus m, that is the LHS of this bottom constraint, will be negative only. Okay. So, therefore, whether delta Ik here takes value 0 or 1, it does not matter, and that is why when Sk is greater than Si, in order to ensure that delta Ik is equal to 1, we have this top constraint. Okay. So, together both of these two constraints will ensure that when Sk is greater than Si, delta Ik is forced to be 1, and when Sk is less than or equal to Si, delta Ik is forced to be equal to 0. Okay. So, in this way we have defined constraints to ensure that delta Ik is defined in the way we want. Okay. So, in the next class we will be continuing this discussion of the scheduling problem where we will be looking at this constraint here. Okay. Thank you.